Hi, Year 11. So I'm going to go through some of the questions that I've assigned you, like usual. We're going to start with 32. I'm going to try and be a little bit quicker than usual because it often takes a bit too much time, and I assume it'd be a bit boring to actually sit here and listen to me. If that's not the case, then let me know, and I can make sure I put a bit more detail and go a bit slower. Up to you. Okay, so 32 has a table of salts, and it says calculate the enthalpy of solution for each of them, referring to table 4.04 to assist. Now, I'm not going to do all of them, but I'll do a couple. So maybe I'll do salt, just regular table salt, lithium fluoride, and silver chloride. So for each of these, you need to remember that the delta H, so that's the enthalpy of solution, is the lattice energy minus the hydration. I'm rushing, as you can see by my handwriting. So we need to look up those two numbers for sodium chloride. So if we go up here, sodium chloride, we have 779 and 774. So this one is 775, oh, 9, sorry, minus 774. Actually, did I read it the wrong way? Lattice energy 779, hydration energy is 774. I think that's the right way I've written. Right way? Yep. Where are we? 779 minus 774 equals positive 5 kilojoules per mole. And that's our answer. Lithium fluoride, probably should have recorded it when I went up there. Lithium fluoride, 1032 and 1005. So delta H equals 1032 minus 1005. Hesitating because I can't remember if that's the actual numbers. Yeah, that's good. 916 and 851. I'll just write them down while I'm there. 916, 851. Okay, this one here would then be equal to 23rd, not 20, what is it? My math is leaving me. So 24, is that 23? 23 plus that is 8. No, 25, 26, 27. 27, that's better. 27 kilojoules per mole. Okay, so that's the answer there. This one here is a greater value than sodium chloride. And silver chloride is 916 minus 857, or no, 851, sorry. And so that would be 50 plus another 15, so 65, positive 65 kilojoules per mole. Now, I'm going to super quickly look up on my other computer to find out the solubility of AgCl, and the solubility of AgCl is equal to 0.0024 grams per liter. The value for lithium fluoride is where are we? It is 0.027 grams. Oh, sorry, that is per 100 grams. So that is 10 times more, so 0.27 grams per liter. And sodium chloride is 360 grams per liter. So as you can see, as this value, this delta H gets larger, it's corresponding with the decreased solubility, because as this number gets larger, it would prefer more and more to remain in the lattice, not hydrated. So this is showing you the preference. Technically, sodium chloride prefers lattice, but not by much, only by a small number. Cool. Oops. What the hell's going on there? There we go. So the enthalpy of solution for sodium iodide, B, is negative 7.5. Describe what this means in terms of its dissociation in water. Okay, so what that means is that sodium iodide would, I'm sure I can spell properly, would prefer, or actually experiences greater stabilization by hydration compared to being in a lattice. It will tend to dissolve readily. Now, if I quickly look that up again, so if I look up sodium iodide, should get a nice high number. Let's see. Oh, nothing jumping out at me. A quick Google search, I'll find solubility. I'm just looking at, oh, there we go. Solubility, just from looking it up, solubility equals 1,842 grams per litre at 25 degrees Celsius. Oops. That is massive. So you can see, again, this number has gone up when the hydration energy becomes, or the hydration becomes the more favorable situation. Okay, so moving on, we're going to go into the enthalpy changes. So we've already essentially worked out some of this already for dissolving things, but we're going to do some more of it. This time we're going to be calculating using our Q equation, which is M delta T times C. So let's give it a go. Remembering that here we have our significant figures, which I've taught you before, so that shouldn't be too much of a surprise. So hopefully we'll get question 33 in before I have to do another part. So it says, calculate the number of joules needed to warm 25.5 grams of water from 14 degrees Celsius to 22.5 degrees Celsius. So that is asking for Q, the amount of energy. That is equal to M times C times delta T. Now M equals 25.5 grams. C is 4.18 joules per gram per degree C. And the delta T is equal to 22.5 minus 14. So that would be 8.5 degrees Celsius. And a positive, so it's increasing. So that means Q equals 25.5 grams times 4.18 joules per gram per degree C times by 8.5 degrees C. Now the grams and the grams, the per degree Celsius and degree Celsius cancel each other out, leaving joules by itself. And if I just put that into the calculator quickly on my computer, on my other computer at least, we get 25.5 times 4.18 times 8.5 equals around, so 906.015 joules. Now we are going to double check. We have our, in the question here, we've got 3 significant figures there. This one here is 2 significant figures. So we may have to, because our values here end up with only, this one only has 2 as well, we're going to end up with 2. So in that case, 910 joules. So that 0 there could be a significant figure. It's ambiguous, it's not really clear, but we are writing it. So 906 definitely has 3 significant figures, so we need to round up to 910. It's mainly because they're not measuring the temperature to enough precision. If they said 14.0 and 22.5, then we would have been able to do an extra significant figure. Okay, so what is the energy released when 75 grams of water are cooled from 100 degrees Celsius to 27.5? Now this time our Q, we know it's energy being released, which means our Q needs to be negative, and we get that from that delta T. So 75.0 grams times 4.18 joules per gram per degree C times by our difference between these two. So 27.5, so 100 take 27.5, so that will be negative 72.5, I believe. Now, hopefully I'm not wrong there. That's, if it was 80, it goes to, sorry, 70 goes to 30 plus another 2.5. Yep. So throwing this into the calculator again, we have 75.0 times 4.18 times negative, oh, actually, I'll times by 72.5 gives me negative 22,728.75 straight up in the calculator, which in this case, we have three significant figures for all of them. So we're going to have three significant figures for our answer. So that would be negative 227. Yep, that's right. So we have that number, which also can be written as negative 2.27 times 10 to the negative, 10 times 10 to the 4. 1, 2, 3, 4 joules. Cool. Now it says here, explain what is meant by the term specific heat capacity. This is just a quick explanation. It just wants you to write that energy to raise 1 gram of a substance by 1 Kelvin or 1 degree C. Now, this is the important bit. The specific heat capacity is grams. The molar heat capacity would be 1 mole. Okay, so I'll pause this here and I'll do the next question in the next part.